So let's put the Jacobian matrix into use, okay? And for that we are going to delve into the topic of linear approximations of functions. But before going into the general case in n dimensionals, let me refresh you what happens in one dimension. So let's do an example. Imagine we have a one-dimensional function f of x equals x squared plus 1. And I want to find a linear approximation at or around x equals 1, okay? So what does this mean? First, intuitively, what does it mean? If we plot f of x versus x, so how does x squared plus 1 look like? So it's a parabola, but it's raised up to x equals 1. So it looks something like this. Okay? So if we want to find a linear approximation at x equals 1, if we find x equals 1, so this is the point at which we want to do the linear approximation. So then this means that we are going to approximate for small values, for values of x that are around 1, this function, this parabola, can be approximated by a straight line, which is tangent. Okay? So this would be the linear approximation. It's almost equal to f of x. Okay? Especially when x is around 1. So one thing we can do is this value of 1, we can call it x0. Yeah? And then we can say that f of x is f of x0 plus delta x. Okay? So for example, if we want to find f at x equals 2, which would be here, then we would say that delta x is equal to 1. Okay? If we want to find it at x equals 0, which is here, then we would say that delta x is equal to minus 1. But normally this approximation is better when delta x is very small. Okay? So if delta x is, for example, 0.1, then we would be at x0, which is 1 plus 0.1, we would be somewhere here. Yeah? And then indeed, if you can see that the red line, which is our approximation, is very close to the actual value of the function. So when delta x is a small number, the approximation is good. Okay? So how would you find this approximation? So it's very easy. F of x0 plus delta x is approximately equal to f of x0, and that would be the 0th order approximation. So if we stopped here, I'm basically saying that I'm approximating the parabola by taking x equals 1, which is x0. So I'm approximating the parabola by the value of the function at x0, which is this value here. So I'm basically approximating it using a constant. Let me picture that in red. Okay. This is a very bad approximation for the function. However, it's not that bad if we are close to x equals 1, right? So if we are in 1.1, then the difference between this and this is not that big. And if we get even closer, the difference gets smaller and smaller. So this is a 0th order approximation. But then the Taylor expansion says we can do better. We can add the first order. So this could be plus the partial derivative of f. Sorry, not partial, because we are in one-dimensional function. So the derivative of f with respect to x evaluated at x equals x0 times delta x. And this is the first order term in the Taylor expansion. Okay? And keeping these two terms, what we are doing is we are writing the equation for this line here. Okay? So let's do it for this particular example of x squared plus 1. What is f of x0? So f of x0 is x0 squared plus 1, right? And x0 is 1, because we are doing the linear approximation around x equals 1. So this would be equal to 1 squared plus 1, that is 2. So let's write 2. Okay, so that's the value of the function at that point. So that's not a good approximation, as we know. This is just a horizontal straight line. So we now want to add a term that is linear with delta x. And this term is equal to the derivative of f with respect to x, which is 2x plus 0. Yeah? So it's 2x, but evaluated at x equals x0, which is 1. So we have to substitute x0 here, and we get 2. Okay? So we can erase this, or, well, let me use a new line. So this multiplied by delta x. So now we substitute this, and we get 2 plus 2 times 1, 2 delta x. Okay? So now we got an equation, which is the equation of a straight line. Okay? So f of x0 plus delta x is approximately equal to 2 plus 2 delta x. And this is the equation of this straight line. Now this equation is written in terms of delta x, but maybe you want to write it in terms of x. So what do? That's very easy. F of x, you just have to substitute the fact that if x is equal to x0 plus delta x, then obviously delta x is simply x minus x0. So you just substitute that here, and you get 2 plus 2x minus x0, okay, which is equal to 2 plus 2x minus 1, which is equal to 2 plus 2x minus 2. So actually it's 0 plus 2x, so it's equal to 2x. So this is the line of the equation that approximates this parabola. So actually I drew it wrong. If I had drawn it accurately, this line would have crossed the origin. Okay? And this is the best linear approximation to this equation x squared plus 1 at the point x0 equals 1. And the way we found it was by using the Taylor expansion up to the first order. Okay? So this is the case for one-dimension functions. So in the next video, I'm just going to apply these same concepts, but in the general n-dimensional case.